So welcome along, ladies and gentlemen, to your weekly SETI seminar. Today we're very lucky to be joined by Richard Carrigan, who's come across to us from the Midwest. Richard did his BS at the University of Illinois and then served in the Army Ordnance Corps for a while at the White Sands Missile Range, and then went back to University of Illinois to do a PhD in high energy physics. Then following Illinois, he went to Carnegie Mellon, where he was an assistant professor of physics for some time. And then after that, he went to the Fermi National Accelerator Laboratory, or Fermi Lab, and he worked for quite some time as a high-energy physicist. He is now a scientist emeritus at that institute and in the accelerator division. He has over 100 scientific publications in the areas of high-energy physics, and the author of several books on particle physics. His career excitements include channeling of high-energy particles, hyperon physics, magnetic monopoles, high-energy scattering, and also, as we're going to hear about today, the possibility of a life and intelligence elsewhere in the universe. So please join me in welcoming Richard.
Adrian has told me I'm supposed to wait a minute or so. That's good, and people can hear me. It's a pleasure for me to be here at the SETI Institute, this fabled center of the search for intelligence beyond Earth. I'm going to talk today about interstellar archaeology signatures. I have a lot of trouble with this word, and I would like to find a different word, but I never have been able to. In particular, I'm going to talk about Dyson Spheres quite a bit in the course of this. I did some of this work I've done in concert with my wife. She supplies the soft side, I suppose you'd say, and Adrian asked me to try to make parts of the talk, at least the beginning, general. So I'm taking you at your word. In pursuing SETI and interstellar archaeology, I like to remember the words of John Wellborn Root, famous Chicago architect, who said, "Reason should lead the way, and imagination take wings from the height to which reason has already climbed." Originally, I thought I might have a picture of Don Quixote or something questing out after things. So we already have seen interplanetary archaeology. The slide on the left shows pictures of the pyramids from the International Space Station, the Egyptian pyramids. And the slide on the right shows parts of the Mars rover and tracks and things like that. But perhaps you should call this robot anthropology rather than archaeology, because it's things that were moving around even then. Now, the talk is going to be organized along the following. Talk a little bit about interstellar archaeology itself. Then I'll talk about, again, a very little bit about the backdrop with the origin of the stars and the Big Bang. Jim Hartle, I guess, is going to be here in several weeks talking about this very contemporary topic. And in fact, the little inset there are the recent results from BICEP of several months ago, where the polarization was observed from the South Pole and shows signs that go back to the very earliest moments of the Big Bang. And also talk a little bit about biological evolution. go on from there to the Kardashev scale, and then talk about some of the effects that are present in the interstellar archaeology landscape. And these include SETI, particularly cultural SETI, exoplanet atmospheres, which of course this institute is very much a part of, a generator of, stellar salting, I'll skip that, Dyson Spheres, main emphasis here, and stellar engineering. I'm going to skip this because even though I like it, I can't find any plausible arguments about how this could really be done. And then move on to the galactic scale, and in particular some ideas of my colleague Jim-Annis and I suppose my colleague Freeman Dyson at some level. The general outline of this was done by Lamarchand some years ago, I guess in discussions with Carl Sagan. As I was looking back at the things that I have, I noticed this wonderful recent copy of the SETI Explorer, and all of the articles in this thing, of course, relate to aspects of what I'm going to talk about here today, and it's so beautifully done. So it's a wonderful chance to be here. Now, Nancy has had several perspectives on this question of the birth of the universe and the stars, and also of biology. Here's her take on the birth of stars. When she saw the so-called pillars of creation from the Hubble some years ago. And of course, up at the top of those columns are big clouds of dust, and stars are popping into existence before your eyes. It's really a remarkable kind of photograph that you see. And Nancy did a painting, a so-called Star Madonna painting there on the your right. And in that, if your eyes are good, you can see the pillars of creation incorporated in that. And as Nancy comments, has it like sun, one of these stars being born, a circling globe with sea fish, bird, and dexterous ape, who's built a clever eye to probe our mysteries? Does her mind escape its bound to ponder ancient light and move a poet's pen to write? Nancy also had a take on evolution and the emergence of life and complex life on Earth. And this diptych here shows on one side the astronomer reaching out to the stars and the planets and asking, can I unweave the gauzy fabric of the stars? While the ant ponders, can I untangle the matted carpet of the earth? There's a missing panel, in a sense, here, and that's the panel of what's the next step from ant to astronomer on. And I think that's, after all, what we're all about. We're talking about trying to reach out, find a sign of intelligence, very likely much more advanced than us, and sort of the scale of the ant is a good thing to go on there. Now, all of this question of a search for looking for effects of intelligence in the universe can be subsumed in the Kardashev scale. The ants would go over there on the left, and a typical ant colony might generate something like 10 watts of power. And what I'm looking for here is yardsticks for measures of what power that's being put out, degree of difficulty, things like that. Ants actually do better than you'd think from a little millimeter slug of stuff running around, because they have hive intelligence. So in some ways, they gain by that, and their behavior, when you look at it, seems more complex than you might expect from such a tiny little creature. Going beyond that, to the next stage is SETI, the core of the Allen telescope kind of activities. And typical power levels there might be 10 to the 6 watts, 10 to the 9th watts, something like that. You do a pick of that. And this will be effect 1 for me. Beyond that, and now getting into the ordinary Kardashev scale, Kardashev number 1, planets, and in particular their atmospheres would be something that we're now getting at some level as far as the atmospheres go, and then we can ask about intelligence impacts on the atmosphere. Third effect will be stars themselves, and Dyson Spheres will be my example there. And the fourth effect, Kardashev number 3, is, we'll talk about galaxies, where the power output is something like 10 to the 36 watts per galaxy. And then, of course, beyond that, you have, in some sense, a big bang with a message from some creator in the recent BICEP results a month or so ago. Now, here's effect 1, the radio SETI paradigm. Phil Morrison and Cocconi many years ago realized that with then technology that you could reach across the galaxy. And the question that you ponder, though, when you start to think about these messages is, are we going to run into trouble? And Nancy and I, we were very young, and thought we were worried about bad messages that left you doing something that you shouldn't be doing. Mein Kampf, for example, would be an illustration in modern times of a message that you got that you perhaps shouldn't have gotten. So we couldn't do anything about it, so we wrote a novel and then moved on to the main parts of our lives. Jill Tarter has noted that with SETI, TV transmissions can go out to something like a light year under current circumstances. So messages are going out to some fraction of the distance to the next star. And an advanced civilization, maybe you could get more powerful TV stations. On the other hand, maybe they wouldn't broadcast. So there are things like that. But in any case, you can detect signals that are cultural in nature. They don't have to be intentional signals that are going to be messages to you specifically as a nearby star or something like that. As far as I know, there's no robust SETI signal that is worth talking about too much. I'm going to, each case, give a little bit of a measure of the degrees of difficulty. One, the lifetime of the signal is something that appears in the Drake equation. Another is this question of power output. And the third is the mass involved. And for SETI, cultural SETI, mass is, as far as I can see, not something that tells you very much. Now going on to the second effect, the atmosphere of exoplanets. And these things might be near to what a Type I Kardashev civilization would be like. We're sort of at the stage now of Galileo looking at Jupiter's moons, who, after all, were his exoplanets, and trying to understand what's going on with them. We're just coming to that. Well, there are modern Galileos. A good fraction of them seem to be women. Sarah Sager and Lisa Kaltenegger, both very active participants there. And all of these people looking at this now have found many signatures of atoms and molecules that could be associated with life. They're the stuff of life. On this planet, 63 light years away, what's the right name for this thing now? But it's got 6 numbers associated with it. In any case, people have found methane, water vapor, carbon monoxide and carbon dioxide, wind, all sorts of things. Spitzer has seen silicon dioxide, which reminds you of computers, particularly when you're walking around Mountain View. But lots of stuff going on here. That it requires very big telescopes, because you've got to do spectroscopy on atmospheres eventually. And you'd sort of like these telescopes to be above the atmosphere, because you'd like to be able to look at infrared signatures. People are doing it nevertheless in other ways. In this particular case, 189733b, it's a hot Jupiter, and Tanetti remarks it's too hot for even the hardiest life, unlikely that cows could survive there. Now the next question, though, about once you begin to look for atmospheres, your next question is what would be a signature of intelligent life in these atmospheres? We can look out toward our own atmosphere and know that there's a signature of intelligence or idiocy, one or the other. We've got a increasing carbon dioxide in industrial times by 35%. And so you can have signatures like this. What you'd like, though, is something that's more specific to invention, if you will. And the freons are one case in point, where we did pump lots of freon into our atmosphere and then got wise and stopped putting so much freon in hairspray. Looking for a freon signature is a very interesting idea, according to Kaltenegger. But you do need these exceptionally sensitive telescopes, and it lies many years out, probably, before we can do this. As far as measures of this, the lifetime of the signature is the lifetime of the constituent in the atmosphere, which can be very long in some cases. And as far as power in the signature, I don't know how to estimate that. But for example, the carbon dioxide burden in our atmosphere is 10 to the 15th kilograms, I believe. And that gives you some sensitivity to the mass involved, substantially less than the mass of the planet, as you'd expect. And I might add that even our carbon dioxide, it's at the 1 in 1,000, so it's not anything like the exoplanet signatures, which are more like 1 in 1 for the cases that have been there. So let's go on then to the Dyson Sphere. Now, the rationale of a Dyson Sphere is to harvest most of the useful energy of the star, the visible energy. And you can, what a Dyson Sphere is you take and you find some planet in your solar system, you break it up and make it into some sort of a shroud that captures most of the energy coming out. You could have a pure Dyson Sphere where the shroud is complete. You close the curtains in the room. Or you could have a partial Dyson Sphere where it's either thin looking through it, or it's only been built around the equatorial region of the star or something. The signature is infrared star with about the luminosity of a normal star. There's a little problem there because of distance. You can't measure very easily the distance of these infrared signatures. On the other hand, for a partial Dyson Sphere, you could hope to look at the star. Well, you can look at the star and see it. Now, the problems with Dyson Spheres, the bad thing, so to speak, is that a Dyson Sphere requires an enormous amount of energy to assemble. It to take apart Jupiter and put it around Earth or around the sun would require something like 1,000 years of the total solar output. This means that if you're going to start from a planet and build a Dyson sphere, you're going to have to bootstrap your way up, and it will be a fairly long process to get where you're going. The second thing that people will say is that a Dyson sphere, a rigid Dyson sphere, is unstable. This would be true. It's a big shell, any kind of perturbation would do it, would disturb it, and it would just, you'd have a disaster. But from the outset, Dyson himself had made the point that some sort of swarm-like thing is what might be involved. Lots of silicon chips, solar silicon chips, for example, might be something that would be there. It's a heroic thing to construct. When I came on the scene, IRAS, which was an infrared satellite that flew in the 80s, had developed a very mature and usable database. And it turned out that IRAS had almost ideal properties for looking for Dyson spheres. It was all sky. It had filters at 12, 20, 60, and 100 microns. And its main purpose had been to look for dust. Well, it was very good at that. And so it was small. It didn't need much angular resolution. But it found lots of dust. In fact, the 160 micron filters were really not usable for my purpose. About the same time, another Earth-based facility came on the air, which was 2MASS. It produced 1,000 times more sources, roughly. And the problem with it is that 2MASS, the best filter for looking for infrared, room temperature kind of infrared, is it's too far away. It's 2 microns, so that you need a source with 10 times the strength of what you can see with IRAS to register in 2MASS. Another feature of 2MASS was it had a low-resolution spectrometer that had pretty good sensitivity and worked for what it turned out I was going to find I had to, wanted to do. I tried using the filters at first, but ran into trouble because of this business of zodiacal dust and cirrus and the 60 and 100 micron filters. And this sort of put me off of filters. But Calgary had prepared an atlas of the sources that were had good low-resolution spectrometer data, and they'd done some degree of classification on those sources, and they had organized in a very interesting way. So I just went ahead and used their classifications to start a search. And I'll just quickly run through how that kind of source went. Let me start from the bottom on this slide, though. There will be all sorts of surrogates, fake Dyson sphere candidates that you can imagine. Protostars like those pictures of that Nancy based her painting on, where stars are being formed, are typical things that will be in a dust cloud. Myras, carbon star-like things exhibit Dyson sphere-like signatures, and many things like that. Some of this stuff can be gotten rid of one way or another, but I mean, you can identify some of these candidates as astronomical signatures. So basically what goes on is you start with a sample of 250,000, then you require the spectrograph, the Calgary set. You get 11,000 things, and then you skip down by making a temperature cut, and the reason for this temperature cut is you'd like to be limiting it to temperatures where life might be operating at. And in fact, the band is fairly large here. 600 degrees would be far too hot, and getting down to 200 degrees or 100 degrees Kelvin is too cold for life. So make a temperature cut, and then select on several of these categories, which includes carbon star-like objects, hydrogen clouds, and so on. And then cut down. You get something like 250, well, you get 1,500 after that. And then you start looking at these sources with the spectrograph. So the spectrograph is being used as a tool here to throw out things which have lines that you might see in a carbon star and this and that. And I used it a little bit as a statistical tool by fitting Planck spectra to the backgrounds, but mostly just looking at spectra to see what's there. And in this process, I came out with a cluster of 16 candidates, lackluster candidates, of which 3 are less lackluster than the others. So this is the process to do IRAS. Here are some spectrographs from this activity. The one on your left here is a carbon star with silicon, I think it's silicon oxide line there at 11 microns. And you can see that the line is very well formed. The spectrograph does a good job on that. There are actually 2 parts to that particular spectrograph. And then you can see the filters are these, the IRAS filters of those black diamonds there, the 12 and the 25 one. And you can fit a color Planck spectrum to that, get a temperature out of it. And it looks like the spectrograph. I don't know quite here what the difference between the absolute magnitude difference was due to. On this slide, on that figure, you can see little triangles on the left down in the 2 micron region, which are the 2 mass triangles. So you can see the effect of the drop off down to 2 mass. And you get a good fit of, for example, a Planck here, distribution here. The slide on the right is the best of this ragtag lot of Dyson Sphere candidates from IRAS. And you can see a pretty good fit of Planck distribution. You can see things that worry you a little bit when you look at this graph, that there may be fluctuations that are lines that you're not accounting for. And those are the kinds of things that happen in all of the ragtag stuff. There are 3 dots here, 4 circles, I should say. And these are from an instrument that flew with Kobe for the black body measurements in about that time. And they don't look like they're, they look suspicious, although the 2 mass things are down where they belong on this. Probably what happened was the angular resolution of this Kobe device was substantially larger than IRAS, and it's picking up another source that's appearing there. This can happen, and that's why you want angular resolution. The little black squares are from a satellite that flew for Star Wars purposes, so it's always a nice adjunct to some of these measurements. Okay, here's a summary of where we ended up on, this is a ATOF plot of the galaxy, and it has the 16, let's call them candidates on here. one of them is sort of shadowing another one, but so if you count, you may come up with the wrong count. But I also added several thousand of the sources before all these cuts had been made, so that this is, in some sense, a representative of what IRAS was producing at that time. And you can see they lie along the galactic plane, but they're well off, some of them are well off of that. And of these 2,000 or so black dots, there's no bulge at the galactic center. So that tells you something about the range of IRAS. It is in the order of 1,000 light years, depending on what kind of object you're looking at. But you've got a reach out that goes well above and below the galactic plane, but doesn't reach anywhere near the galactic center. The lines here show the region that Arecibo operates in, so that only one or two of these sources came within the range of the SETI searches from Arecibo. So you can't, looking at this, you can't rule out or say something about this one had a known SETI source with it. Of course, there are no known SETI sources anyway, but you can't place lower limits on what was seen SETI-wise. Okay, as far as the degree of difficulty here, the lifetime is the lifetime of a Dyson Sphere, and this might be very long, depending on how actively or how people understood how to keep a swarm of stuff up there. The power that's involved is the power of a star, 10 to the 26 watts, typically. And the mass that's involved is, let's say, the mass of an Earth, 10 to the 24th kilograms. Okay, so one thing, it would be very hard if you saw an IRAS candidate for a Dyson Sphere. You've got to have additional information, and this was recognized many years ago by, for example, Carl Sagan. And so SETI would be one handle for that. You find a candidate, an IRAS candidate, and you go look for a SETI signal from it. And several of us, Peter Backus, who was with this institute at one point, Jim-Annis, my colleague at Fermilab, and I did look at some of those candidates. And here's the best candidate, so to speak. And you see, you don't see anything sticking up enormously here. And you know, a little more thorough investigation was done of that. Of course, there are cell phones on this, people signaling to you. And there's this nice shoulder, but all the people at the SETI Institute understand this shoulder. It's clouds of things in the same vicinity with slightly different Doppler shifts. Okay, moving on to the fourth effect, galactic scale signatures. And why are these things particularly attractive to think about? It's very hard to imagine, at least for me to imagine, getting a SETI signal from another galaxy. It's just the power involved is really not right. So this is one of the better tools, the only tool I know of that you can hope to look beyond our galaxy for signs of intelligence. What would be a signature? Well, one signature might be a galaxy filled with Dyson spheres, or partially filled. And if you had that, what you'd see is little, what I call Fermi voids, where the visible light had been eaten up and turned into infrared. Now, let's go back for a step and think about how you would fill a galaxy with, say, Dyson spheres. one thing that people often get hung up on is the question of whether it's practical. Does this involve faster than the speed of light travel? The answer is no. With just Voyagers that have left our solar system in the last year or so, if you'd only increase the energy of those Voyager missions by a factor of 100, in other words, the velocity goes up by 10, you could have been across the galaxy in 60 million light years. This is nothing. I mean, the galaxy's only made a half turn or something. So Enrico Fermi is purported to have recognized this about the time of World War II, and then raised the question, why don't we see aliens here on Earth? And this Fermi paradox is a real challenge for this question of, I suppose, SETI overall to answer. It's a tough one. Both Dyson and my colleague Jim-Annis have observed that if you just go and you look at spirals, our galaxy, our spiral galaxy doesn't look like it's had lots of infestation from Dyson spheres. I'll show a slide on this point. And Annis also has looked at this, looked at several nearby galaxies, and made the same point that the nearby galaxies don't look infested. On the other hand, Jim-Annis had a different attack, and he used a process that the astronomers among you will understand, but I can't, called the fundamental plane. And this fundamental plane paradigm, what you find is that a plot of the log of the brightness of galaxies versus the log of the size follows a straight line, fits that straight line very well, and without too much scatter. And Annis, who's an expert in galaxies, did this for 106 elliptical galaxies, and found that there were no outliers that would have, say, only 25% of the light from a normal elliptical galaxy. Now, why ellipticals? This is for ellipticals. Annis also did this for spirals. And in fact, the spiral argument is easier to understand for a non-astronomer, I suppose. But he looked at the ellipticals. Why ellipticals? Well, ellipticals are considerably more regular in appearance. So you think to yourself, maybe if I find a little void, I'll have something more to hang my hat on. Okay, so what's the degree of difficulty in this signature? The lifetime is, say, a stellar lifetime, although if you've got a galaxy completely infested with Dyson spheres, for example, you might, you'd have an ensemble of different stellar lifetimes and things like that. The power output is about 10 to the 37 watts. In other words, 10 to the 37 stars with shrouds around them. And the mass involved is something like 10 to the 36 kilogram, 10 to the 11th planet, say. Okay, so this is now Jim-Annis and his point of view here about let's try elliptical galaxies because they're easier, they're lots more regular. Here's a picture of the Whirlpool galaxy, 30 million light years away. And what I tried to do here was look at regions that you could construe as void, just naive, most naive kind of thing you could do. And start looking for unexplained voids. I mean, this is all void at some level, but let's look for unexplained ones. And when I did that, something like 5% of the voids could be, might qualify as unexplained. And what you'd hope is when you see a void, that it's filled in with infrared stuff, and the voids that you do find here are not, they're not standing out in infrared. So let's move on to Annis's point about ellipticals. Here's a very beautiful elliptical taken in Australia, and this is in the is invisible, and you can look at that and you see it is quite uniform, and there aren't a lot of features there that stand out and say something's going on. Now the next couple of slides are ponies for me because I don't know much about galaxies. But a lot has changed. What you knew about galaxies 10 years ago is, chances are, a little bit out of date. And in particular, this Atlas 3D collaboration, Earth-based or ground-based astronomy, but looking out and doing what are called integral field observations, where they divide the galaxy into a raster, and they look at individual lines in each raster and get rotation rates of the galaxy that way. And what they found was that perhaps 2/3 of the galaxies you see and think are infrared, or elliptical, sorry, I've got infrared on my mind here. You think are ellipticals turn out to be instead fast rotating disks with perhaps some of the dust spun out of them, so that they divide early type galaxies into two kinds, fast rotators and slow rotators. Sloan, which dear to anybody from Fermilab because of our involvement there, has also made classifications on galaxies that had modified the old Hubble tuning fork paradigm here. If you're looking for some place to come up to speed on modern galaxies fast, this course by Mushatsky, is it, at Maryland, includes things like the recent Atlas 3D things. It's very useful. Now, the questions you're going to ask yourself about these ellipticals when you start to look at them is, one, can ellipticals support life at all? Some of the early studies of habitability for spirals and, incidentally, ellipticals took the point of view that you have this sort of homogeneous behavior of stars rotating around in there, but maybe there's going to be a lot of disruption in that picture, and you won't form planets properly. So maybe ellipticals are just bad for looking for life. And then you need to ask, what are some of the other reasons for voids? Understand this. Well, generally speaking, skip the first part of this. It's mainly for me. Let me just talk. There are pictures of habitable zones in galaxies have been developing now for about a decade, more than a decade. If you go back to Rare Earth and Ward and Brownlee. I think the early studies came out with habitable zones that were quite narrow for both, well, particularly for spiral galaxies, which were being studied. And I think over the years now, as people have learned more about exoplanets, these things have gotten less conservative than they were in the past, and have developed through better and better models. And in fact, Gowanlock several years ago has a model which he feels he could extend to ellipticals. There's no big problem in extending it to ellipticals. Probably the problem is that all these modelers have bigger fish to fry, and they don't want to fry your fish. So how about then the inhomogeneities in the ellipticals? And my colleague Steve Kent, who's again another galactic expert at Fermilab, says, fond of this aphorism, if you've seen one spiral galaxy, you've seen one spiral galaxy. If you've seen one elliptical galaxy, you've seen them all. So that was Jim-Annis's point, I suppose. The factors that give rise to the inhomogeneities are, there are lots of rings that you see for one reason or another. Nearby globular clusters, of which there can be lots, perturb the surface stars, or the sort of nominal surface stars. Their surface fluctuations, the stars themselves shine, their dust lanes. And just looking through casually, I mostly found sequential rings as the things that go on, and I'll show you one in a second. But the thing that the process, the experimental aspect of the game is that you want both infrared, good high-resolution infrared photographs, and you want good visible resolution. And in fact, you don't really have as much of that as you'd like. The Hubble is probably the best place. The Hubble infrared only goes out to several microns, but it has typically something like a tenth of a pixel, or a tenth of an arc second kind of resolution. And so that what you do see when you start to look at this in detail then is this problem of pixelation is going to be hard. The way you'd like to do this is with differential subtraction, where you have a good photograph, more or less the same resolution of the visible, and a good photograph of the infrared, and you subtract one from the other, or you make a model that does the same thing. So here's M105, and people have gone through, modeled this actually with spheroids, and so you can do background subtractions from spheroidal models that they have. And here's the data that's available with this. The green is the Hubble, and you can see it shows a much better pixelation resolution, if you will. And the black, I think, is the Spitzer, which is not bad. For example, Weiss is worse than Spitzer. But, and then the blue points are Sloan points at visible. And you can see that features come out best in the Hubble. The red is a fitted spheroidal thing by Gebhardt, I think. Okay, moving on. Here's that same galaxy, not with a cross-cut, a radial cross-cut across it looking at densitometer numbers, but just seeing. I've tinkered with the grayscale here to try to bring out pixels a little bit more. And you can see the pixels, you can see how you can begin to see little individual blobs at the sort of 10%-ish level and the pixel level. The lines, the azimuthal contours are fitted contours, fitted to every 2 pixels, and the variations in those contours radially out is something like, can be 10%. Now here's that same galaxy, but with background subtracted using the spheroid, and lo and behold, there is a ring in here that's it's something like 3 arc seconds diameter. The image is 5 arc seconds across, and again, these are with these excellent Hubble pixels here. So a few months ago, Jason Wright came here and talked about his idea, I think it's called Glimpse, which is to go and look for alien heat sources using WISE. Now, WISE is to some extent like the IRAS filter things, but the filters are closer together as far as their spacing in microns, and the angular resolution is just much, much more, and of course there's a lot more sensitivity, so there are lots more sources. So this is a very interesting idea he has. He also talked when he was here and is preparing, I think, to publish ideas about the backdrop of all this. And I should once again emphasize it's not just Dyson Spheres that you can talk about here. You're really making, when you start to look for things shifting into the infrared, you're making a more general statement than a particular model involving one kind of signature like a Dyson Sphere. So I think this is an interesting project for him to pursue. And then just to summarize, it's a very busy slide, so I'll just touch on the high spots. And in fact, maybe what I should do is just speak to the radar plot in the upper left-hand corner. This tries to show on a log scale one of those degree of difficulty measures. And in this case, it's the range, the reach out range that you can have for the signature. And as you can see, by far the best signatures to reach far out are galactic scale signatures. This almost doesn't need to be said. It's so obvious that it would be so. So even though these galactic scale signatures are hard to do, they're worth, I think, some thought to continue to investigate them. So then we close with a summary here. We can, for interstellar archaeology, we can look for cultural signals from SETI, still probably, well, it's nearly possible even now. And we can look for cultural planetary atmosphere signatures. And we've been making great progress, to my thinking, on atmospheric signatures. We're to the point where we can begin to ask ourselves, are we going to be able to see signatures of life? Intelligent life is another matter, and it's going to take many decades to get into that particular place. Dyson spheres are tough, but at least it's worth some thought. And if there was another, perhaps the Weiss data can tell us something more about that. Perhaps we should go look at Spitzer for more data that's there. So as we are at the stage of Galileo, we're just getting to the point where we've found our exoplanets, we've found perspectives on all these things, and it's not going to be easy, but I think we want to keep looking for these signatures, and signatures beyond SETI and cultural SETI. If I could draw from the perspective of another Chicago poet, Larry Janowski, who was height challenged, Larry said, "I wish I were taller, but when looking at the stars, it doesn't matter." Thank you.
Okay, if you can put up your hand and I'll get around to you with the mic. Dick, if I could ask the first question, as about slide 15 where you were showing the IRAS signatures of your candidates. A little before that. Yeah, so the question mark. So what is it about that spectrum on the right that you were really feeling there were questions around?
Okay.
What made it an imperfect candidate?
I think there's lots of scatter in those points. And in particular, there is a peak at sort of 11 microns. On the other hand, there's no statistical thing in that observation. You know, I'm just saying that bothers me about that particular case. And again, the problem of those circle points there from Kobe, is it MERS or something, is there.
Okay.
Hi, I have two questions, so I'm going to ask two, and you just decide how you'd like to answer them. So the first question is about the near future. So where is this research with Dyson Spheres is going? You were talking about the exoplanets which are being discovered through only NASA and Kepler. They announced 715 exoplanets. Maybe there is something, you also were talking that it's good to have different perspectives on the same subject. Maybe Kepler and looking for infrared signatures, something that will help us to narrow down, you know, this bunch of exoplanets and see the ones which are in habitable zones and may have something. So that's question number one about near future. And question number two, you talked a little bit about the atmospheres, and you talked about importance of metallic planets, right? So because of the atmospheres, the challenge is to understand, you know, what's underneath the atmosphere. Is it a metallic planet? Is it a gas giant, possibly like Jupiter or Saturn, that have their own energy, right? So it's not just the energy of the star that we're dealing with, but we also are dealing with remaining energy from the planet formation. So the question there would be kind of how do you account for the fact that we don't know about the structure of the planet? So it may be not just the star energy that comes into play, but some remaining planet formation energy that comes into play and how it affects understanding of Dyson spheres.
Okay, to answer the second question first, I think there are probably many people in this room, I'm sure there are many people in this room that know about that. I don't know about these, all these questions about formation energy, questions of high Z materials in there. I'm a total babe in the woods. As far as the future of Dyson Sphere research, I think Jason Wright's WISE search is a good one. Going on to look at the Spitzer stuff in a little more detail would be a good thing for somebody to do. Going back and trying to answer these questions about these criticisms, if you will, about Dyson Sphere construction. This would be a good class for a bunch of students at MIT to address, in somewhat the same spirit that Jerry O'Neill once took a group of freshmen or Princeton students for a semester and had them answer what would a space station look like, you know, a big space station. I think whether that's, oh, and you made one other point, the point about Kepler's bearing on this. I have not looked at where the, well, you know where Kepler is, after all. So it's a relatively small part of the sky. And forgive me, I haven't gone and looked at that galactic plot and said, here's Kepler, and there are no things nearby. Or use that as a tool to, say, try to focus the search. I think it's a good idea.
Hi, I also had a question about this slide. You know, you're rejecting in your narrowing down of candidates, you're rejecting the ones with spectral features like that. But in an artificial Dyson swarm, couldn't you have spectral features that were due to the material that whatever is, you know, solar arrays or whatever?
For example, silicon would be, and that is a silicon oxide or silicon dioxide feature. It's a good question. I don't have that ready an answer for it.
Hi, on the slide previous to this one, I saw that you were kind of reducing the number of Dyson Sphere candidates to 0. And then a couple of slides past this, if you go forward, I think 1 or 2 slides.
I'm sorry, where is the 0?
Well, below the 3, I guess, it
Okay.
seems to be approaching 0, right?
It's going toward 0,
Yeah.
yes.
And then if you forward a couple of more slides.
Am I going in the right
That
way?
one, yes, that slide, it says there were 6 sources near Galactic Center that are curious. And I was wondering what makes them curious and how that relates to the previous slide going towards 0.
Okay. These are the squares and the circles are the 16 things on that previous slide. The squares are the 3 least unlikely, if you will.
The bottom of that other slide.
Yes, yes, down there. Now, what was your question, your point again?
The 6 curious and how do they...
Oh, okay, right. That they're at the galactic center. And you see, because I argued to you that the black dots, which are earlier, 2,000 things at an earlier stage of the elimination, just to get a big sample, not necessarily things that would qualify as my Dyson spheres, but a big sample. And that they didn't peak around the galactic bulge, where if you had an instrument that could reach out 10,000, 10 kiloparsecs, say, then you'd expect to see the galactic bulge as a big blob there. And I was just surprised in thinking about this and preparing this talk to say, why haven't I looked at that before? And now she's raised this point about why haven't I looked at the Kepler region. I may have looked at it at some point and forgot I looked, because Kepler is easy to look for. It's a small region here.
You're plus 90.
Where is Kepler?
Yeah, you're plus 90. Not too far. Yeah, so the square and circle might be just...
To look at, okay. So,
Okay, if there's no further questions, Dick, we have a special SETI mug there. It has a couple of perhaps participants in a Dyson Sphere conversation, whispering each other the Drake equation. Please join me in thanking Dick for his great talk.
thank you.